Assalamu alaikum. In this video, I would like to share a reverse engineering problem in FSM, finite state machine. Because most of the time, we were given a straightforward problem like sequence detectors, vending machines, and traffic lights, in which we begin with this state diagram and proceed with the state transition table, and then finding the Boolean expressions, and finally we construct the logic circuit of the system using flip-flops. So this is the problem. As I mentioned before, this is like a reverse engineering problem. Actually, it is taken from the textbook, Givon, page number 437, question number 7.2. Okay, so let's begin. So we are given the circuit, and the task is we need to construct the state transition table and then construct the state diagram based on the given circuit. So obviously X is the input and Z is the output. So we are given two flip-flops which are D type, D flip-flops. So we can name the output of our flip-flop with any variable. So let's begin. Okay, so let's name this the output of the first flip-flop as A, and the output of the second flip-flop as B. So A is basically the MSB, so B is the LSB. So as we mentioned before, X is the input. Here we have X, and Z is the output. So the input for the flip-flop that produce output A should be DA, and this one should be DB. Alright, so basically this should be A bar, and this one is B bar. Okay, so we can write down the Boolean expression of DA, DB, and Z. So DA equals to, based on the connection, so this is B goes to here and with X bar, so DA equals to BX bar. So DB equals to, there is an OR gate here and two AND gates. So this is B, B, and this one is actually A bar. So A bar, B, X bar, or, so the second AND gate gives A bar, B bar, X. And Z is simply equals to AB. Okay, from this expression, we can know that the system is actually a Moore machine, because the output Z is not explicitly the function of inputs. As can be seen here, there is none of the what you call input X appear in the expression. So this is a Moore machine. In which the output is solely depends on the present state. Okay, so let's begin with the let's proceed with the state transition table. Okay, so I rewrite all the expression that we have. So dA equals to bx bar. So dB equals to a bar b x bar, or a bar b bar x. So actually this expression can be simplified like, let's say we factorize a bar, so we have bx bar or b bar x. So in fact this is actually equals to bx or x. And thirdly we have z equals to AB. So we can fill up our state transition table. So in the leftmost column, this should be the present state. And the next column should be the input. So the present state is A, B. The input is X. So we can fill out this state transition table. A0, okay, because A, B, the state is 2 bit, the input is 1 bit, so the combination of them form a 3 bit variables. That's why we need to have 8 rows in our state transition table. So next, the next column should be the next state, which are denoted with A plus and B plus. The next column is the flip-flop. So we have 2 flip-flop, one for A, another one for B. And finally we have the output, which is Z. Okay, so far we have the expression of dA, dB and Z. So we can fill out this table because Z equals to AB, so it means that these should be 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 0. Okay, for dA, dA equals to bx bar. So where is bx bar? So the only time, so it's when bx bar equals to 1 is when b 1, x 0. So here and here. Okay, then dB. dB equals to a bar and bx or x. So whenever a equals to 1, dB equals to 0. So when a equals to 0, dB equals to bx or x. So 0, 1, 1, 0. Okay. So we can fill up this column. Since a plus equals to dA, b plus equals to dB, we can just copy all the value from the next column. Alright, so we can proceed with the state diagram. So before that, we have to understand that AB represents the states. Means that when AB equals to 0, 0, so this actually corresponds to state 0, state 1, state 2, state 3. So we can construct the state diagram which consists of 4 states. So this is state 0, state 1, state 2, state 3. As I mentioned before, this system is a Moore machine, so we need to label the output inside the circle. So Z equals to AB means that the only time the output is high when the state is state number 3. So else the output equals to 0. Okay, next we can proceed with the input flow from one state to another. So let's refer to the first row. So the present state is 0, 0, which is state 0. When input equals to 0, the next state is still state 0. So we can draw this kind of line. So when x equals to 1, state 0 goes to state 1. And then we can proceed. State 1, input 0 goes to state 3. State 1, input 1 goes to state 0. Next, state 2. When input is 0, goes to state 0. Goes to state 0. State 2, when input is 1, goes to state 0 as well. So 0 or 1. State 3, when input is 0, goes to state 2. And when input is 1, goes to state 0. So that's it. So we have constructed the state transition table and the state diagram as well. So that's all for now. Thanks for watching.